This is the second in my series of lectures on statistics for nuclear medicine, in which I'm going to be talking about probability distributions. Probability means the chance of a particular result happening. We can calculate probability by looking at the frequency, how often a particular result happens, and divide that by the total of results. That gives us the number of results expressed as a fraction of the total, which is how the probability is defined. So for example, if we look at the data which we've seen before on the frequency of number of bone scans each day, we have a frequency distribution showing frequency on the vertical axis against the value, in this case the number of bone scans done each day, on the horizontal axis. We had a total number of observations of 10. There were 10 squares in this frequency distribution because we had 10 days on which we made our measurements. So the total in this case is 10, so we can convert frequency into probability dividing by the total, which is 10. So for example, if we take the value 3, we did 3 bone scans with a frequency of 1, so 1 divided by 10 is 0.1, so the probability of doing 3 bone scans in a day is 0.1. Likewise, 6 bone scans in a day occurred with a frequency of 5. 5 divided by 10 is 0.5, so the probability of doing 6 bone scans in a day is 0.5. Now when we added up the total number of squares under the frequency distribution, we got the total number of observations of 10. If we add up the probability of all the squares in the probability distribution, then we must get a total probability of 1, because that means certainty, that means something happened, and we know for certain that we did somewhere between 3 and 6 bone scans in every day, so the total probability must come to 1. The total area under this histogram of the probability distribution must add up to 1. Now, the probability distribution defines the probability of obtaining a given result from any measurement. It can take any shape, and it could be a discrete value, like the example we've just been looking at for the frequency of doing different number of bone scans in a day, giving us a discrete probability distribution. Or it could be a continuous curve, like the example here, where the probability varies continuously because the values aren't discrete numbers like 1, 2, 3, 4, but can take on any continuous value. Both of those are valid probability distributions. The distribution doesn't necessarily need to be symmetric in shape. Indeed, we can see our bone scan probability distribution here is rather skewed to the right, and this continuous distribution is rather skewed to the left. But in all cases, the area under the curve or under the discrete measurements must add up to 1.0, because the total probability of something happening has to be 1. Now, although any shape can occur in principle, in statistics certain shapes occur quite commonly. And during these lectures we shall be looking at several of these, and what I'm going to discuss in more detail in the rest of this lecture is the binomial distribution, the Poisson distribution, the normal distribution, and the t-distribution. So that brings us to the end of this first part of introduction to probability distributions. In the next part we'll look at the binomial distribution.